Hello, my name is Andrew Francis. I'm going to talk to you about choosing optical equipment for bird watching. I've been a bird watcher for about 30 years now. I've worked as an ecological consultant for about 5 years and as a volunteer for the RSPB for a year. So I know a few things about using and choosing optics, so I'd like to share those with you today. So what do you need? Well, the first starting point as a bird watcher, you'll need a pair of binoculars. And binoculars come in a variety of magnifications. Some of them will go to really very high magnification. It's possible as astronomical equipment be like 20, even 30 times binoculars. And some zoom binoculars advertise enormous magnifications as well. What I'm talking about here is a hand stabilized pair of binoculars. Something that's very easy to use, quick to get on the target. You're viewing with both eyes. It's an entry level kind of a thing, something that any bird watcher will want. So a suitable magnification for hand stabilization is typically anything up to about 10 times. Usually above that it becomes increasingly the case that the magnification magnifies the kind of handshake that you have, particularly if you're somewhere windy, and it becomes quite disconcerting to look. So yeah, typically a magnification of 7 till 10. I tend to use a monopod quite a lot, and I actually use a pair of 12 times binoculars a lot of the time. But one thing you will want with your binoculars is a rain guard to keep the rain off the eyepiece lenses. Extremely useful. I prefer the single piece designs, but a lot of binoculars come with a device that's kind of hinged in the middle. I find it a little bit of a nuisance because I like to be able to flick it on and off just with my thumb, and it's better as a one-piece construction in my opinion. So the other thing you'll want is a neck strap. So you sling it around your neck, and the wider that neck strap, the more comfortable it will be. It's very useful if you're looking at birds in the distance in what I would describe as open habitats, such as estuaries, mudflats, open water, to have a telescope so you can view birds. Quite often they're gregarious birds, and in big flocks they're very easy to flush. One bird gets scared, they all go. So a telescope's very useful. So very often you'll have to make a choice. Do you want a fixed lens or do you want a zoom lens? Now traditionally fixed lenses were of better quality than zoom lenses. It takes a lot more technology to put together a good zoom lens and to create a good fixed magnification lens. So certainly in older scopes and less sophisticated scopes, you're probably better off using the fixed lens options. But a zoom is a very useful thing because you can kind of choose a trade-off with what kind of magnification you want. It's a trade-off between field of view and brightness on the one hand and magnification on the other. So if you do get yourself a telescope, you'll want something to stabilize it with, typically a tripod of course, and ideally means of carrying that tripod such as a backpack can be very helpful. And there are various bits and pieces that you can take with you that will allow you to use your telescope as a high magnification camera. I tend to do quite a lot of phone scoping, but I also like to carry a camera with me as well because mobilizing and aiming a telescope can be quite fiddly. It's great for very high magnification distance views of things, but it tends to be that you have quite a small aperture, which means that anything that's moving quite rapidly is likely to blur and will be quite hard to get on focus on. So a camera is rather better for closer range stuff. So I personally use a mirrorless interchangeable lens camera because they're a little bit smaller than what is the professional standard of a digital single lens reflex camera, which is what most wildlife photographers, certainly all the professionals, use. There's another option as well, which is a bridge camera. That's a kind of camera that has a single lens that performs a variety of different tasks, whether it's macro, close focus stuff, or zoom into the distance. So cameras are increasingly used by bird watchers. Sometimes people will go out and find a rare migrant or get a quick photograph of it. It was too quick, they didn't know what it was. Through their binoculars they weren't sure. They go back, blow up the pictures, zoom in on the primary feathers and get some idea of the wing length and all kinds of feather detail that they couldn't really have picked out in the field, and claim a rarity. So bird watchers are increasingly using cameras, even aside from appreciation of nature, as a means of recording what they see and getting it accepted if it's rare. So the starting point is, what kind of magnification do you want? So as I say, binoculars are hand stabilized. I have a pair of 12 times that I use quite often, but I tend to use those with a monopod. My regular go-to pair of binoculars are 8 times binoculars. Some people prefer 10s, that's fine. Telescopes much higher magnification, so they definitely need stabilization. So the objective lens is basically the larger lens in your pair of binoculars or your telescope. So that can measure, it's measured in millimeters. It tends to vary between 20 to 60 in binoculars and maybe 50 to 100 in telescopes. Now I would tend to suggest that any binoculars with something less than 30 millimeters as an objective lens are not likely to be a great deal of use. I'll get onto why later. It concerns the exit pupil diameter. So how much magnification you have is related to how much you need it to be stabilized and how much field of view you have. What the exit pupil is, I'll come on to that later, and a property called depth of field. Now depth of field is about the range of distances over which you have a sharp image when you're focused on a particular object. It can be quite nice if you've got a flock of birds to be able to simultaneously view birds at different distances, and it can also increase your ease of getting onto and in focus onto a bird that's moving rapidly. So it tends to be that higher the magnification, the more you need them stabilized, the smaller the field of view, the smaller the exit pupil, and the smaller the depth of field. So lower magnifications have some advantages as well. So field of view and magnification are kind of inversely related. Absolute field of view is certainly. There are various measures. Degrees are most commonly used. Sometimes I'll quote meters at 1,000 meters, sometimes feet at 1,000 yards. I tend to think of things in degrees, so I like to divide them by these factors to get what that comes to. There's another measure, which is the apparent field of view. That's always in degrees. You can obtain that by multiplying your magnification by the absolute field of view. Now the apparent field of view is quite a useful metric if you want to compare different magnifications fairly. So for instance, you might have a lower power pair of binoculars that has a wider field of view than a higher power pair, but then the apparent field of view is what it looks like when you're looking through it, and it's quite nice to have an image that feels quite roomy. It's just a psychological thing really. It's more pleasant to look for. It's less like you're looking through a keyhole. So when people talk about wide field instruments, they tend to mean for a level of magnification. So as a rule of thumb, it's generally the case that an instrument with a 65-degree apparent field of view is regarded as wide field. So for a 10 times pair of binoculars, that would be something like 6.5 degrees. So exit pupil is very important. Now a human pupil ranges in size from between 1mm to 7mm depending on light and age. In low light your pupil expands and allows in more light to help you deal with the darkness. So if you see these two binoculars in the middle, they have different sized exit pupils. Now the idea is that if you're your own pupil expands to be larger than the exit pupil of your binoculars, it's like it's asking for more light than you're being supplied. So it's a good thing to know what kind of a minimum size of an exit pupil you need in different light conditions might be. I find that for most viewing conditions you don't need anything above 4. Sometimes in low light it would be nice to have a 5mm exit pupil, and people who tend to be out in very low light conditions might even want a 6mm or even a 7mm exit pupil. But it's also worth bearing in mind that in order to have such a large exit pupil, you either need to have a lower magnification or a larger objective lens. So it's actually possible to calculate the size of your exit pupil by dividing the objective lens diameter, that's the large lens, by your magnification. It tells you how big this exit pupil is. So I wouldn't tolerate an exit pupil in a pair of birdwatching binoculars of less than 3.5mm. You can get a reasonable image with telescopes at smaller exit pupils than that. But you do find if you're using a zoom eyepiece, for instance, as you zoom up you see the exit pupil get smaller, and eventually it starts getting quite dark. That would actually give you a rough idea if you read off the magnification on your zoom eyepiece and divide your objective lens diameter. It will give you a rough idea of how big your own pupil in your eye might be in those conditions. So it's probably worth mentioning as well that, for instance, this pair of binoculars on the left-hand side, this is a pair of binoculars that I have, they're 8x56s. If you have a large objective diameter, you tend to have a heavier optical instrument, partly because you will have larger prisms as well. Now, prisms are elements within an optical assembly that are designed to correct for a natural tendency of the two lenses working together. Your eyepiece lens and your objective lens will yield an image which is flipped from left to right and from top to bottom. So that would be terrible if you're trying to actually follow a wild animal. So prisms are designed to rectify that. So the first design that was used to deal with this was called a Porro prism, and it was named after a Polish scientist called Porro. So Ignatius, I think, Porro. So this is the simplest design. It relies on something called total internal reflection, and the upshot of this is that it's a very, very efficient means of transmitting the light, because it doesn't require any silvered surfaces to reflect the light. The same applies also for abyconic roof prisms. These also rely on total internal reflection. Now, talking about roof prisms, what a roof prism is basically you'll see on these two prism designs are kind of keeled shapes. On the Abyconic you can see it at the bottom of the diagram, and the Schmidt-Pekin you can see it at the top of the diagram. Now there are some consequences to this. Both of them, you'll have a separation of light from the right and the left hand sides of your image that will end up being polarized in a different direction, and the result of this is that when they're brought back together they will interfere with each other and reduce the contrast of your image with sharpness. So means of dealing with this was introduced when they came up with what was called a phase correction coating, which they apply to one side of the prism. That is something that is sometimes missing on cheaper roof prism instruments, but was introduced in I think the early 90s or late 80s. So if you look at older roof prisms than that, they tend to be less contrasty than certainly than Porro prisms from the same era. So it's a useful coating to have. So the Schmidt-Pekin roof prism has an additional issue in that it needs to have a semi-silvered mirror. it doesn't rely totally on this very efficient process of total internal reflection. It needs a semi-silvered mirror, and this can be accomplished with a variety of different coatings which have different levels of reflectivity. Now, silver was reckoned to be a highly reflective coating, slightly superior to cheaper aluminium coatings, but the downside is that silver, particularly, and aluminium to a lesser extent, quite often tarnish when exposed to oxygen. So sometimes it's necessary to create a sealed optical environment. Potentially it's purged with nitrogen or argon or something like that, which helps preserve the coatings of the prisms. So there is a more expensive kind of coating which is called a dielectric coating. These tend to have the most reflective coatings of all. They're more sophisticated and difficult to make. So as a rule of thumb, it's worth saying that Poro prisms are good value for money because they're a simpler optical system to implement. The downside is that very often it's hard to waterproof them. It's much easier to waterproof roof prism binoculars because the focusing mechanism is internal, whereas if you focus a pair of Poro prisms, you will see the eyepieces move in and out of the body. Now, there are some marine binoculars that are Poro prism design that are fully waterproof, but they tend to have separate eyepiece focus, and that's not really very helpful. If you're trying to follow something rapidly, you certainly don't want to be focusing two eyepieces, so you do want a centrally focusing mechanism. So Schmidt peak and roof prisms actually form the majority of the market these days, and usually including the very most expensive pairs. Now, I feel that Poro prisms are generally better value for money, potentially less waterproofed. Some people don't like the shape of them, they don't sit as comfortably on your chest, for instance. They look a bit old-fashioned. Some people are concerned about that sort of thing. You have iconic roof prisms because they're total internal reflection. They are used by people who maybe don't want roof prisms but would still like very high light transmission. So very often they're used in hunting binoculars. So coatings are extremely important. Now you'll see this picture on the left hand side, a couple of pairs of binoculars with very different coloured coatings. Now what coatings do is they actually reduce the reflection of light from a surface. So if you have an uncoated surface, you lose roughly 5% of light each surface it passes through, and some optical systems can have 10 or 15 surfaces in them. So if you do the maths, then you'll end up with only about 60% of the light actually being transmitted. So you'll have a darker image, and you'll also have problems with stray light that tends to be reflected back into the optical system and turn up in places that you don't want it, and really reduce the quality of your image. So these different bloomings tend to be made from magnesium fluoride. They're intermediate optical density between your optical glass and the air, and that reduces the amount of reflection you get. You will find that light tends to be reflected more when it comes obliquely onto an optical surface. So looking at these binoculars, the coatings look quite vivid, but you're looking side on. If you look straight into them, they tend to look a bit less vivid. So you'll see this picture of a graph of a spectrum for transmission of light and various high-grade pairs of binoculars. So they are typified by having a reasonably flat kind of transmission curve, which means that you get a nice color balance. So your whites look quite neutral, they don't look reddish tinged, they don't look bluish tinged. They should be quite an even kind of a color. These, as I say, are like really good quality binoculars. So your very best models will have 85% transmission across the visible spectrum and not a great deal of variation. Cheaper models will have substantially less. It might be, 70, 75, 80%. So good quality coatings are very important. They improve the amount of contrast in your image because they reduce the amount of stray light you have ruining your image. Yeah. So optical distortions are worth mentioning as well. You will understand more when you have a look through a pair of binoculars and actually start having a look for some of these forms of distortion. First one to mention is one called chromatic aberration. Chromatic aberration is an issue created by the fact that light tends to be split up according to the different refractive indexes of different wavelengths of light. So blue light on one hand and red light on the other will be focused at a different point. So that means that you end up getting kind of color fringing, a bit like a rainbow, on cheap optics that are badly corrected. So there are various methods that are used to try and correct for this. What you see in that picture is a simple one lens kind of an optical element, but you'll find that in binoculars there'll be at least two elements, and a so-called achromatic double, or perhaps something slightly more sophisticated. There are other strategies as well. There are materials which, for a unit of light bending, which is the purpose of the lens, is to bend light into a new optical plane. For a certain level of bend, there will be less difference between how much bend is put on each end of the spectrum. So materials that have these properties tend to be referred to as extra low dispersion materials, or high resolution optical elements, or a good example of these is fluorite, which isn't actually a glass, it's a crystal. It's very expensive and is used in very top quality optical equipment. So there are other forms of distortion. You'll see in the bottom figure on the left a diagram showing how straight lines can be distorted. So there's barrel distortion and pincushion distortion, and I have read that a little bit of pincushion distortion can actually be helpful when you're scanning, because there is a slight tendency, because of the optical properties of the human eye having a slight barrel distortion, that you will have things kind of lingering on the edge of your optical field, and it's quite disconcerting and unpleasant. So sometimes it's actually deliberately built in a little bit of pincushion distortion, because people's eyes vary. How that looks in the real life can vary also. You can test the level of distortion, particularly you'll see more at the edge of the visual field, by looking at a nice straight wall or straight roof or something. Check that it's straight first, it isn't always. There are other forms of distortion as well. Spherical distortion, it's caused by different levels of magnification. For they come to different planes dependent on what part of the lens they hit. There's a thing called comma. If you see this picture, it's of stars, and it's showing this kind of a comma shaped streak. Other ones call it, well, it's astigmatism. I don't fully understand all of these phenomena, but it's worth mentioning that they tend to occur at a greater level on the edge of the visual field, and that the more magnification you have, the more likely you are to be able to see them. So this is also worth bearing in mind when you ask yourself the question, do I want an extra low dispersion, high resolution, fluorite type optical equipment? How useful that is kind of depends on how much magnification there is. Because to be honest, you can correct images very, very well at low magnifications with any of these, without any of these highfalutin optical elements. But you'll find that if you're using a high magnification eyepiece on a telescope or something, it can be a real godsend to have like a fluorite element or something. So I actually feel that it's more important to spend large amounts of money on a good telescope than on a good pair of binoculars in some ways. So Eyecups are worth discussing. Come in different types. The old-fashioned type in the middle was a fold-down rubber eye cup. That kind of has the purpose of your eye cup really is to separate your eye from the lens to a sufficient distance to be comfortable. So if you're too close, you get this effect called kidney beaning, which means that a slight movement sends shadows across your visual field and you kind of lose sight of things, and it's quite disconcerting and unpleasant. However, if you're too far from the eyepiece, then you get an effect called vignetting, which is basically the edge of your field will look a bit fuzzy, and you're not actually seeing everything that your binoculars will allow you to see. So until binoculars started fitting fold-down rubber eye cups or rotating eye cup rings, it was often the case that people with spectacles were unable to see the full required visual field. And I have been told as a spectacle wearer, oh, you should fold the eye cups right the way down. You should twist them all the way down, but it's not necessarily the case because people wear their spectacles in different ways. It's best finding out what's comfortable for you, and a lot of these rotating eye cup rings have click stops which allow them to be adjusted to the same kind of distance on each side, which helps you to look through them straight, which is really quite useful. Now these winged eye cups on the right, these are designed for non-spectacle wearers, but they're quite useful in that they will keep peripheral light from coming in and causing extra reflections inside. It can be useful in low light conditions, high contrast conditions. So, how to assess optical quality? It's good to go somewhere and try a range of binoculars. You're better off with a largish optical store, preferably a specialist one. A lot of RSPB reserves have these kind of things available. You can go to a small camera store if you want to, but you'll typically find that the selection there is focused towards cameras, and that very often the people don't really know how to stock good quality binoculars at a certain price point, and sometimes they're not very well versed. So go to a specialist place, somewhere where you can test it against real wildlife and have a nice view. It's a good thing to do. It's often been said that you should test binoculars in low light conditions, but I really don't think that's particularly necessary, because if you have a pair of binoculars that will behave properly in high contrast conditions without reflecting lots of stray light into your light path and reducing the contrast, it doesn't go milky when you look towards a bright light source. These also tend to be the kind of binoculars that will look quite bright in low light conditions, though you do need to bear in mind what the exit pupil is. So yeah, there are advantages to testing in dull conditions. There are advantages to testing in bright conditions. Ideally, you'll have one of those kind of really contrasty kind of days where you have some bright sunshine and some dark areas as well, and you kind of get a variety of different conditions. Definitely look at silhouetted objects. That's what you want to look for. That's where you want to look for chromatic aberration. You will find some images will be sharper than others. Sharpness tends to be how precise a border is that you're looking at. Contrast is a slightly different characteristic. That's more about the difference between the brightness of very dark and very light areas of your image. So you can potentially have quite a sharp image which is actually low contrast, because it might be that you have stray light in the optical path which will make the darker areas look brighter than they should be. So you'll tend to find as you look through a pair of binoculars, that the peripheral areas at the edge of the field of view are of the lowest optical quality, and that the inside is of the highest optical quality. Now, a lot of optical manufacturers advertise, they say things like edge-to-edge sharpness, and they boast about this. And you know, it's nice to have sharp edges to your field of view, but it's also worth bearing in mind that if you have a choice between a wide field instrument that has a very wide usable area and a narrower field one with a sharp edge, you're probably better off with the ones that have a slightly sloppy edge, because that's still a usable part of the field of view. It might be something that makes a difference between missing a bird and or getting on it properly. So wide field is certainly a very useful thing, particularly if you like bird watching in closed habitats like woodland, and you're chasing things around at close range and they can rapidly move out of your view. There are additional checks you can do just to get some sort of an idea about how well implemented various optical ideas are, just by looking down the inside of a barrel. You can look from the objective lens and see if there's any dust in there, see how hygienic the thing is, because if you've got dust in there, that's obviously going to reduce the quality of your image. It might not do it by much, but it can do. Also, blackening of the insides, that's important, because it reduces the likelihood of stray light coming in from the edges, messing up your image. So it's nice to have well blackened optical tubes on the inside. You can look at the pupils as well. Sometimes you might find that they're not entirely circular. They might be slightly ovoid. It suggests that they're what they call truncated, which means that some of that light from the prism is being lost somewhere in the prisms. It tends to happen when you have prisms that are not quite large enough. It's usually because they're trying to keep the weight down in a pair of binoculars. You might also find as you look down against a dark surface, you see the exit pupil, but you will also see smaller areas of light within the optical assembly. It's best not to have too much of that. It tends to indicate that you will have stray light problems. But the proof of the pudding really is in the eating. So decide, how wide a field of view you want, how far you can out into that field of view you can accept there to be a kind of a slight optical deterioration. Look at close focusing as well, particularly for binoculars rather than telescopes. There are other considerations. Price, of course, is important. There is a law of diminishing returns. If you pay over a certain amount of money, you will find that with each increment of money, adding more and more to it is making less and less difference to your optical quality. So you will find, for instance, a difference between a £400 pair of binoculars very often and a potentially £3,000 pair of binoculars can be quite small. But probably the difference between say £100 pair and a £200 pair can be substantially greater. So yeah, you'll find you can get a good pair of binoculars really quite cheaply. If you are buying a fairly cheap pair for say under 150 quid, it definitely would always recommend a Prism pair. I have a bit of a thing for Prisms. I feel you can get very good value for money from them. They're not necessarily waterproof. That may or may not be an issue. It's good to be honest with yourself. I mean, people like to think of themselves as outdoorsy and dedicated and what have you, but the fact is you need really horrible conditions for that really to matter, and usually that's something I would need to be paid to be out in. I have had binoculars leak on me before in really horrible conditions, but it doesn't tend to happen. So is that important to you? Is it not? It's your choice. Good build quality can be indicated by how smooth the focusing mechanism is as well. It's also worth considering how do you feel about wearing this pair of binoculars. Now, I actually quite like wearing bizarre looking, archaic looking binoculars that I know are optically really good, as opposed to going for a fashionable, extremely expensive pair, because I kind of feel if you throw enough money at something, you will get yourself a good pair of binoculars. But really being discerning and buying a cheaper pair that does the job for much less is much more of an achievement. So I take some pride in having mid-price optical equipment that are very high performing. But some people might get home and then think, oh, I wish I'd gone and bought that pair of Swarovskis or what have you at 3 times the price, and be disappointed, and then maybe a few years down the line we'll get an upgrade. Fact is, though, there are all kinds of things that will make far more of an effect on the kind of vision that you have. Just simple light conditions and fieldcraft, knowing what direction to approach a wildlife from. Haze, optical haze can make a difference as well. In fact, it's worth bearing in mind when you think about what kind of magnification you might need for a telescope, for instance. I very, very rarely find that anything above 60 times would be useful, not just because you would need to have a huge objective lens and very heavy telescope really to get a decent amount of light from that, but also because if it's really that far away, you need to magnify it that much. By the time you can actually see that object properly, there's going to be a hell of a lot of air between you and it. So if you have a bit of haze in the atmosphere, a bit of rain, you're not going to see it at all well anyway, and you're just going to be magnifying a blur. So yeah, for terrestrial telescopes, people rarely go beyond 60 times. If you're looking up into the atmosphere with an astronomical telescope, you're actually potentially looking through a lot less air, because the density of air, of course, decreases as you go further and further towards space. But that's not what we do as bird watchers. So I'd also like to direct you to some other resources. A particularly good reviewer are Albinos, which are a Polish site. They write their articles in English and their reviews. They are the most technical reviewer on the internet. They're terrific. They have a useful article about how they review binoculars, explaining the ins and outs as I've done, but in more detail, and a very nice article on colour rendition and coating. Another good site to go to is Holger Merlitz's website. He's a German authority on optics who's written a book in German about binoculars, but I don't read German unfortunately, but he does have a good website. So when you looking, you might want to go on eBay and look for a second-hand pair possibly. So it's nice to be able to go online and have a look for a reviewer. And it won't always be the top reviewers who are able to offer you an opinion about a pair of binoculars, but you still want to have a go for it anyway and see what you can get, because it's kind of fun. It's a bit of a gamble. So it's important to be able to assess reviewers and their level of expertise. So the first question I would ask is, do they have a basis for comparison? If you've got a reviewer who's testing it against a fairly decent pair of binoculars and can offer an opinion comparing and contrasting, that's much better than someone who is just reviewing a single pair of binoculars. So it's very good when you have people who will review loads of binoculars at once. It's also you will find some reviewers will go on and on about all of the different specifications. Oh, it's got ED lenses. Oh, it's got dielectrically coated prisms. This, that. It's got this, that, and the other. And really, they're not talking about the optical quality. They're talking about what they think the optical quality should be on the basis of the materials used. And you will find that they're sometimes quite different. For instance, my optically best pair of binoculars have the highest light transmission of any production pair of binoculars, and they're Poro Prism. They don't have any ED elements in them, but they're absolutely terrific. So it's not just about all the gadgets and gizmos and extra special materials that are used. It's also good to bear in mind that sometimes when people buy a pair of binoculars, they want to justify the expenditure to themselves. The next day they'll write a rave review about it, and then 6 months down the line they'll think about it a little more and they'll be like, tried someone else's and yeah, they were a bit better to be honest, and maybe I didn't want to buy them. So the older a purchase, the more reliable the review from it is likely to be. It's also good to just check that they actually know what they're on about, because not all of these reviewers do. There are misconceptions, things like thinking that the field of view will increase with the objective diameter. Now it's actually quite often the opposite case. Certainly in the 8x class of optical instruments, you'll find that a little 8x30 or 8x32 binocular tends to be a very wide field instrument. You can have like an 8-degree field of view with those, but if you have these big hunting binoculars with an 8x56 or something, 6.5-degree field is more typical for those. So it's actually the opposite, and you'll find people making this mistake quite often in reviews. There are other people who seem to think that talking about viewing in ordinary conditions, that having a large exit pupil, it will look really bright. That isn't the case at all. It shouldn't make the exit pupil shouldn't make any difference. What will make a difference is how good the coatings are, because that will influence the apparent difference between the brightness of the dark areas and the light areas by reducing the amount of scattered light in the optical system. And you'll find people who recommend models with small exit pupils or zoom binoculars, and you definitely know straight off that they don't really know what they're talking about. So good luck with all that. I hope it's been useful. Thank you for your time. If you want to leave any comments for me, please do. Yeah, thank you for listening.